So hi there, I'm Diana, and I am an iOS developer at Thoughtbot. I'm here to talk about a few examples of computational statistics and a little bit of machine learning in Swift. Keep in mind that at my day job, I am an iOS developer and not a mathematician, probably like a lot of you. So judge me on my correct use of the word tuple, and not on me maybe mispronouncing the word Bernoulli trial. Today I'm going to go over a few different applications of models and formula in Swift. We'll touch on some machine learning concepts as well. In our implementations, we'll put the language through its paces and get to use a few fun features of Swift. We're going to get to use Swift today to solve some problems that we usually don't get to see during our day-to-day work building Mac and mobile apps. So, get excited. First up, we'll be calculating a ranking system for data points based on pre-existing scores. After that, we'll create a classifier for text using probabilities derived from our training data that we already know the classification for. Then we'll use a naive summarization algorithm to summarize paragraphs of text by surfacing only the most important and most relevant text from the whole document. Lastly, we'll create a Markov Chain text generator by creating a model, teaching it our entire data set, and then traversing through our model to generate text. I should quickly mention our data set. Our data set will be anime descriptions, titles, and ratings. By the end of this talk, we'll have a library that can rank different anime according to ratings, can classify what genre an anime is in based on its description, can create totally new descriptions and titles for fake anime, and can summarize long descriptions of anime into terse, concise summaries. Okay. That's what I had the most fun on, I'll admit it. So let's talk about calculating a rating. I am not the greatest expert at anime, but so when I choose a show, it's usually just because one of my friends has recommended it. But this is the age of the internet, and word of mouth is dead. And let's just see how we can automate rankings instead so that I don't have to rely on actual people. So our problem for this first part, for this first example, is that we need to sort items by rank, where our items are anime titles. We're given the number of positive and negative votes. However, we can't be exactly sure that the rating that we see from those votes is perfectly accurate. So when I say accurate here, I mean how close the observed score is to what its true score is. And when I say true score, I mean the score it would have if everybody saw it and everybody rated it and didn't accidentally click the wrong button or something. So we have to somehow account for the overall quantity of votes, because we can assume that as we get more votes for something, we can be more confident about the rating being exactly what we are observing. So we're going to use the lower bound of a Wilson score interval. There are a few different solutions, but this is the one that we'll be using today. We're using this interval based on the fact that we want to use a system that is pretty skeptical about any rating that is based on very few votes. Let's look at our implementation. First, we want to create a simple protocol that allows any object to be rateable by having vote tuple, up and down votes. Our use case for ranking is for collections of objects. So we get to create an extension on collection type where all of our elements conform to the rateable protocol. You can see we use the sort function here, but we're passing it the lower bounds of our confidence interval because we're being a bit pessimistic. So let's look at now our implementation for the Wilson confidence interval. We're returning here a tuple of our lower and upper bounds that we mentioned before, even though we're only going to use the lower bounds. If you wanted to be very optimistic, you could use the upper bounds, but wouldn't be advisable. The inverse normal cumulative distribution function, the INCDF there, is just a constant for whichever confidence level you require. So 95% is very common, so you could just use a static number for Z, a constant number for Z. So our lower bounds and our upper bounds here just rely on Z, the positive number of positive votes, and on the total number of votes. So you can see here, being able to use special characters is very helpful and very appropriate when you're implementing mathy kind of formula. So let's use our rating protocol that we created and our Wilson score. Here we create an anime that conforms to our rateable protocol, and we create new instances of the class with the vote tuples. So when we sort our list of these anime structs by Wilson ranking, they rank themselves quite nicely. You can obviously do more than just two, but that's all that fit. So now we're going to talk, now that we know how to rank our data, we're going to talk about classifying our data. The first step to classifying is to tokenize your text. So I've determined that the only anime that I want to watch is anime about giant robots. So I need a way to filter out any anime that is not in the genre that I like. The first step to classifying our data is to represent our descriptions so that we can model a correlation between all genre A anime and a different correlation between genre B anime. So to do this, we will use a bag of words model. Each anime description in our training data set will be broken down into a set of all of the words it contains. We strip out non-specific words like and, it, the. Then we determine which words will occur most reliably in text that is known to be in a specific category. So for example, the word space appears often in mecha genre anime descriptions. We're going to be using the Bernoulli document model to classify our anime. Bernoulli trial basically just means you can have two different outcomes. So our two different outcomes would each be a category of anime. The first step is to tokenize our text. Basically, we're creating a usable bag of words that excludes particles and pronouns because those are not helpful domain-specific words. The tag is significant function here excludes all of those non-relevant words. I used a nested function for that one just because it's a small, hyperlocal, singularly relevant function that's only part of the tokenize function. After enumerating through all the linguistic tags and only inserting words that are relevant, we have a workable bag of words here. For now, all our classifier has is a variable that is our training data set. Our training data set is keyed off of the classification of each piece of data. We already know the classification of all of the data that we're putting into our training data set because it's training data, and so that's already known. Now that we can create tokenized representations of our anime descriptions, we can classify new pieces of text. So, for example, we could determine whether an anime description should probably be classified as a magical girl or as a giant robot anime. And again, that's a Bernoulli trial because there's two. We'll be using a naive Bayes classifier to classify our text. This means that the probability of each word occurring in the text is independent of the probability of other words occurring in the text. Here we have our lazy variable that creates vectors of word probabilities using the keywords from our training data set. We're not technically creating vectors here. We're actually creating dictionaries whose key is the relevant word and whose value is a probability. So the probability there is the word probability for each classification. So for example, the word robot is in 66% of giant robot anime descriptions. So its word probability is 66%. Its word probability for magical girl anime is entirely separate. We're calculating these probabilities and storing it here in this loop. So now that we have our training data set classified and our probabilities from that data set calculated and stored, we can create our classifier. The first step is to create a type alias for our classification type. So this gives us the flexibility to classify practically anything, or at least anything that's raw, representable, and hashable. Inside of our classifier, we're type aliasing the generic type C to classification just for convenience. Inside the actual classify function, we create a maximum tuple that is going to be our result. So the tuple contains a classification and a score. These will end up being reset to the highest calculated score in our for loop. So let's run through the for loop just for a giant robots classification. Our probability starts off at 1.0, which is 100%. But if you had a prior probability that, say, 80% of all anime is always about giant robots, you could use that instead. For each word that we actually have a word probability for, we check if the text that we're classifying has that word in it. If it does, we multiply the overall probability, which started out at 100, by that token's word likelihood. If it doesn't, we multiply the overall probability by the opposite of that word's likelihood. So basically, that word's likelihood of not appearing in a giant robots anime description. If the probability that we calculated for the giant robots classification ends up being higher than the magical girl classification, then the maximum will be set to the giant robots tuple. And then at the very end, we'll just return the classification that had the highest calculated probability. If it's giant robots, then I guess I would end up watching it. So. Now that we can classify anime descriptions, let's try our hand at actually summarizing anime descriptions. So, has anybody seen Akira? I don't know if I'm saying that right. Okay, so I see some recognition. That movie is crazy. People told me it's a classic movie. It's a must-watch film in anime, but so confusing. So so we're creating a summarizer now. At the end, we'll use it to summarize the movie Akira. So data summarization is technically machine learning, and today we'll be using a nice, simple implementation of that. To summarize our text, we want to find a representative subset of all of our sentences that we believe contains the information that's in the whole set of sentences. So to determine if a sentence is representative of all of the sentences, we'll compare it to every other sentence in our text. If the sentence is similar to many other sentences, we can say it is highly representative. We'll measure similarity between two sentences by how many words that they have in common. So a sentence with many words in common with other sentences is very representative and will most likely end up being in our summary at the end. So let's start by splitting our text summary into pieces. By the way, this slide and all of the next 3 slides are just extensions on string. So here we have 3 new vars that return a string divided by paragraphs, sentences, and words. We'll be using just paragraphs and sentences, but alternatively, you could use words. These all return an array of strings. The method enumerated substrings with options just calls enumerate substrings in range with the provided option. Our next extension on string returns the representative score of all of the sentences in our string. So we loop through every sentence in our string. We then calculate and record a score for every sentence. A sentence's representative score is just the sum of its intersection with each and every other sentence in the text. We could have normalized our score based on the length of the sentence so that shorter sentences could be weighted against longer ones, but I rather like that this here is a bit biased towards long sentences with a lot of words. So that's a preference. After we've looped through all of our sentences, we will return the dictionary that just contains all of their representative scores. Now, let's actually take advantage of the way that people actually write. So paragraphs are usually reliable delimiters between subjects within a document of text. So let's use our previous var scores by sentence, and then let's split our text by paragraphs. So for each sentence in that paragraph, we can check its score in our scores by sentence dictionary that we just created on the last slide. And we can return only the highest scoring sentence in each paragraph. After we append all of the highest scoring sentences from each paragraph, we have our final summary. So let's use our summarizer string extension on the movie Akira. Using a 6-paragraph summary, this is what we get. Each sentence is the most relevant sentence from each paragraph. So as you can see, it's a pretty high level, pretty decent synopsis of the movie, even if some of the references to he are a little ambiguous. But I guess reading this synopsis I'm only as confused as I was when I actually watched the movie. So, the scene where the guy explodes, like, I like that it's one sentence here and not, I don't have to see it. So, last up, we're going to be creating a Markov chain text generator. A Markov chain is a model of possible states that includes probabilities for transitioning from one state to another. The probability of moving from one state to another has to depend only on the current state and not on any of the preceding states. So you may have seen Markov chain generators before, especially on Twitter. They use your old tweets, and then they tweet back at you in your own words. But most of those, I think, are in JavaScript, so we'll see one in Swift. We'll use our Markov chain model to generate new anime titles. In our model, each state will be a word, and the current state will be the current word, and the next state will be all possible next words. The probability for which possible state we transition to is just going to be random. To represent this model in Swift, we'll just use dictionaries where the key is the current state and the value is an array of possible next states. So in our Markov object, our memory variable is the actual Markov chain that we will create and teach using our anime descriptions. First, we need to define a seed that will represent the beginning state and ending state of our model. The seed can't be a word or letter that could appear in our text. I was using an emoji, but that did not render quite correctly. So the learn function splits up text words by word and adds each word to the Markov chain. So that's the first function there. So here we can see how a word is learned by adding it to the memory model. We learn words by looking up our state, which is the previous word, and then adding the new word to the array of possible next words, or by creating a new array. So let's use our model to actually generate a sequence of words. We will traverse through our model using random probabilities when choosing the next word. So our very simple ask function here, where we recursively query our Markov chain for the next state, we'll at the end then join this chain of states together to form a new description. The lookup word function that we just saw randomly selects the next random state, given the current state, and then recursively calls itself until it encounters the seed, which signals ending the chain, so the end of the sentence. So I don't know what you could call Voltron, but if you could pun that in Japanese with Swift, that would be awesome. So now we've written implementations of rating, of classifying, of generating, and summarizing text in Swift. Now we can use all of these little mini frameworks that we've created to build an app that ranks, automatically classifies, summarizes, and generates new anime. A fun note about specifically tokenizing in Japanese is that you can, if you strip away everything except for the kanji, which are like the characters, the root characters, then that's essentially the perfect way of tokenizing a sentence or a piece of text, because you have no conjugation on a kanji. You have no, I think, plurality. It's a root word, so that's perfect for tokenization. So to conclude, Swift is an amazing language for creating iOS and Mac apps. But given its ease of use, it's also a great tool for learning new concepts, like the ones that we just went over. I got to test this theory, and I think we got to test this theory today together by going through a few fun, new, one-off examples in Swift. Despite the fact that I'm speaking in a language that is non-native for, I think, a good number of you, we can actually have a pretty thorough discussion of the examples that we've just gone over, because, firstly, of the unreasonable efficiency of really simple implementations of machine learning and statistical concepts. They're not perfect, but they're pretty darn efficient. And also because the programming language that we're using it's quite elegant. Theoretically, we could have built all of these using Python and some of the very beautiful libraries that they have available in that language, but I dare say it would have taken a bit more time. So in the implementations that we've gone over, we've gotten to see examples of little gems that Swift has to offer when you're trying to write code that is very flexible and is very reusable. That trait is extremely necessary when you're creating an implementation of a formula that can classify any object or sorts generic objects. So we've gotten to use certain features of the language that are really indispensable when you're modeling a couple of fun statistical formula. So thank you for letting me channel all of our passion for this nascent language into doing something a little bit fun and a little bit different than most of our day-to-day challenges that we get to see working on iOS and Mac apps. Given that Swift may someday become our backend, our language of choice for building backends, and also the fact that Python can't reign supreme as the king of natural languages and natural language processing forever, it's worthwhile to just kind of try our hand at approaching some backend type and computationally intensive problems in Swift. You can't read it probably from there, but it'll be available on the slides. There's some further reading, a couple of fun academic papers on stuff that you've just seen. So yes, thank you so much for listening.
All right. Hey, thank you, Diana. Fascinating talk, and really amazing to see how far we can go with a few core concepts. What really struck me there is how much this process kind of explodes the strings and really kind of creates a lot of in-memory objects. Do you know what the memory implications are of doing something like this with a large body of text, and if there are ways to apply certain strategies to minimize that impact?
So quite frankly, when I was implementing these, I was not using incredibly large data sets, so I didn't really see any lag from that. All of these were originally just implemented right inside of a playground, which ended up obviously having a lot of overhead, so that was very slow, but that's just for kind of hacking it out. I think mostly that's exactly what I was trying to illustrate in this talk, is just you can just hack it out, and even though it might not end up being the most efficient method, it's really just a tool for learning specifically. And so if you wanted to do a pretty deep dive, you'd probably want to explore things like that.
Okay, very cool, thank you.